So today, we'll be talking about managing applications the Kubernetes way. Before we get started with the session, I would like to do a little show of hands exercise here. How many of you are using Kubernetes at work or in your setup? Wow. One more. How many of you are using stateful workloads in Kubernetes? Great. So this is actually a perfect session for that then. So, so today we'll be talking about how to extend Kubernetes to manage your workloads on it. So my name is Sunil Arora. I'm a software engineer at Google. I've been working with Kubernetes for over 2 years. I've contributed to projects like kubectl, Kustomize, and most recently, I've been focusing on Kubernetes extensibility. And I'm a tech lead and maintainer for Kubebuilder project. And with me, we have June T, who is a software engineer at Google, working on the Kubernetes team. So the way we have structured our talk today is first, we'll be going over some of the Kubernetes basics, some of the core patterns that we use to write built-in APIs and controllers. And then we'll be looking at some of the ways to extend Kubernetes, specifically focusing on API extensibility. And then we'll be diving into Kubebuilder, the SDK, which is how do you build built-in API, how do you build APIs and controllers. And then the favorite part of our session, which is the demo, and we'll be showing you a SqIDB operator, an example demo here. And we'll try to keep 5 to 10 minutes at the end for the Q&A. So with that, let's get started. I'll invite June to talk about what is the Kubernetes way.
Hello, everyone. My name is Jun. I'm also a software engineer at Google Cloud. For the past few years I work at Google, I work on Kubernetes controllers and operators. And I'm eager today to share with you all about the basics of Kubernetes, which we will cover in the first session. Kubernetes, as you all know, is a container orchestration system that automates deployment, scaling, and management of containerized applications. It groups all the containers belonging to an application into logical units for easy management and discovery. It builds upon many years of Google's experience in running production workloads. It is able to be run on major public clouds like GCP, AWS, Azure, and with the latest technologies, it is also able to run on the on-prem clusters. It handles all the common cluster routines like scheduling of nodes, the lifecycle, scaling, etc. on behalf of users. Kubernetes is an API-centric system. What this means is that everything communicates through the APIs. The API server is the center of universe in Kubernetes. It powers all the APIs. It serves the REST endpoints, supporting all the common cloud operations like creates, gets, updates, deletes. It also stores the API resources, the objects, in etcd. Almost all the components in Kubernetes, such as the client like kubectl, the control plane component like scheduler, and the node agent like kubelet, have to talk through the API server. They have to send a request to the server for processing. Now, let us have a view at the basic building blocks of Kubernetes. In Kubernetes, we have this concept named pod. A pod is basically a group of tightly coupled containers belonging to an application and the shared volumes. We group all the containers of an application together and also the necessary underlying volumes between this pod. And all the containers between the pods share the same life cycle and phase. So if you have one pod, if a pod is down, all the containers between it is also down. And the containers also share the same IP and pod space. They see each other as local hosts. There are three types of containers: the init containers, main containers, and sidecar containers. Init containers perform initialization routines like creating data directory or downloading the source codes before the main container is started. The init container has to be completed before we can start the main container. Main container is where the real application is running. For example, as an end user, if I deploy a Redis application, the application will be run between the main container. And lastly, the sidecar container is a container that provides additional routines and functions to assist the main container. Some examples are monitoring and logging sidecar. One of the most important features in Kubernetes is that it allows the end users to specify the desired states, the target states, the states that they want of the cluster to Kubernetes using declarative APIs. This means that the users only need to tell the Kubernetes that how many replicas that they want, and Kubernetes will basically do everything, perform the reconciliation underneath automatically. This is different from imperative API, in which the users have to provide step-by-step instructions. In Kubernetes, all the API resources, all the objects have an API that can be broken down into 3 components. The first component is metadata, in which you can put the name, namespace, the labels, etc. And the second component is a spec. Spec API fields is where the users provide the desired states that they want for this particular API resource. And lastly, the status field is where the Kubernetes will update the current status, the current states at current point of time of the API resource. For example, what is the number of pods that is already ready at this moment, and how many of them is still not ready yet. Now, let us go to another important concept in Kubernetes, the controller. A controller is a long-lived control loop that performs the automatic reconciliation on behalf of users. The reconciliation is made out of 3 steps. First, the controller observes the existing current states of the cluster. It then compares the states with the desired states, the declared states provided by the users. It deduces the differences, and then it acts upon the differences by bringing the cluster to the desired states. For an example, let's say we have a cluster, and that cluster runs 2 application instances. However, the user specified that there is a need to have 3 number of replicas running at any given time. So what happens here is that the controller will create another replicas to make sure that the total number of replicas is always 3. Similar thing happens. Let's say initially we have 4 replicas. The controller will then delete one of the extra replicas. And now, let's go over some primitives in Kubernetes. Primitives, or the built-in controllers of Kubernetes, is widely used for running the applications. I believe most of you have already used them. I will go through some of them. The first one is replica set. Replica set is a controller that maintains a set of pods, of identical pods at any given point of time. It guarantees availability of a certain number of pods. If a pod is down, it will always restart it. The next control is deployment. Deployment is a little bit complicated, but it is a higher level controller that provides declarative updates for the replica sets and pods. What happens is this: when a user creates a deployment resource, a corresponding replica set resource will also be created by the deployment controller. And then the replica set controller that we mentioned just now will create the pod. Hence, the deployment controller will manage all the pods indirectly through the replica set controller. And lastly, it is the stateful set controller. A stateful set controller is used specifically for managing the stateful applications. When we mention about the stateful applications, we refer to those applications that depends on the data states for to run their operations accurately. Yeah, all the pods between the stateful set maintain a sticky identity. that has a persistent identifier that will be remain the same throughout any rescheduling of the pod. For the first part of the stateful set, we have the index number 0, and for the second one, we have 1, and so on. For the next session, Sunil will guide us through the extending Kubernetes.
Let's look at how Kubernetes have evolved with respect to running applications. So initially, it started with stateless apps, which are very simple apps. And if you look at the operations involved in managing the lifecycle of stateless apps is on day 0, you would just orchestrate them. And day 2 would pretty much require either scaling them up or down, or would require updating, which is a rollout. So those operations are supported by the existing primitives like replicas and deployment. You can just use those, and they are good enough to run stateless workloads. Now, moving on to simple stateful apps. These are apps which are not distributed. They are kind of very simple to run. So for that, stateful set and CSI gives you good enough primitive to run them successfully for day 0 and day n operations. Now, let's look at a complex app, which is, think of a distributed application like a data store, or let's say a messaging application like Kafka. So on day 0, it involves orchestration, which is setting up the initial topology. Day 2, typically, that's where the real trouble starts, which is, let's say you want to take backup or you want to restore. Depending on the application may have its own storage semantics for that. Now, update might involve, like these applications have their own clustering mechanisms, so update might require a lot of coordination between the nodes. Similarly, when it comes to scaling them, which is you want to adjust the topology, so that would also require coordination between the nodes. It gets really complicated. And so it goes on. You want to reconfigure the same thing. So if you have such an application, now this is beyond Kubernetes knowledge to provide primitives to operate these independent applications. So what would have been really nice if you could model all these operations of these complex applications as declarative APIs, and you can use the same tooling like kubecontrol to operate on them. And so for example, here, it would be nice if I want to launch a DB instance, I could just set, here is a spec from my DB instance, which is read replicas as 2. Storage is, I want this sort of storage. I want backup to be done weekly. I want backup storage to be using slow disk and things like those. And I can perform all those, I can manage all those operations using the kubecontrol API, tooling. So Kubernetes doesn't give you those primitives, but it provides these extension mechanisms which you can use to build such an experience on top of Kubernetes. So let's look at when Kubernetes was started. It was started with the goal of being just a container orchestration system. But over the years, what I've been seeing last 2 years, team and community has put in so much effort in making the system extensible, and now it has evolved into a platform. So it provides constructs which you can build on top of. So because when it comes to running application, it is just not running application within Kubernetes. There are a lot of stuff which is around application which people have to worry about. It is policy enforcement. It's about continuous deployment. So I think with evolving it as a platform, I think there's a lot of pieces that community has contributed, if you look at that, is making the whole platform really powerful as well. So there are 2 dimensions to extending Kubernetes. One is infrastructure extensibility, which is extending it to different hardware providers, different storage providers. The second is API extensibility, and which is what we'll be focusing on today. So in the next few slides, I'll be covering the 2 main important API extensibility mechanisms, and then we'll go back and reconnect with the slide we talked about earlier, how to manage the complex application. So the first primitive is custom resource. And you must have heard of this term SqIDB everywhere. So custom resource is nothing but is another API provided by Kubernetes, which allows you to introduce your own API in the cluster. And to give you an example, so custom resource definition, how do you do that? So custom resource definition is another a declarative YAML file. You specify the sort of what I would call schema for your custom resource. Think of it as, let's say if you have database, a SQL database, you would define, when you create a table, you define a schema and then you have rows in the table. In the similar way, CRD is the definition, is the schema for your API, and custom resource instance are, think of them as the actual instances for that resource. So let's say once you have this YAML file, which defines the schema for custom resource, where you can specify the API group, the version, and the kind. And then there are additional features that CRD supports. For example, open API validation. You can specify what fields, what sort of validation needs to be performed. Then printer column support, which I'll cover later when I do a live demo. So the way to think about this is once you submit this YAML file, then Kubernetes API server gives you this hosted endpoint service. It will automatically create REST endpoint for that API resource. And now this API is available to all the existing tooling and clients in order to consume. So the experience is very similar to what you will have for built-in APIs. So the second primitive extension point that Kubernetes provides is the admission webhooks. So if you look at the lifecycle of a request in the Kubernetes API server, let's say an incoming resource like pod, when it hits the API server, it will go through the series of admission control plugins. There are some built-in admission control plugins, but there are two new ones which got introduced in last year or so is validating webhook and mutating webhook. So let's look at one by one. So validating webhook is where Kubernetes API server for each incoming resource can make a request to an external HTTP web service, and that service can say whether to accept or reject this incoming resource. Now this can be used to implement some very powerful mechanisms, like let's say you want to enforce certain policies in your system, which is a simple example would be you want to allow only certain images to be running in Kubernetes. So this would be one way to do it. Let's look at another extension point, which is mutating webhook, which is, so let's say you have an incoming resource like pod, and if you, Kubernetes API server will call another HTTP API service, which can mutate the spec of the incoming resource. So in this case, let's say you can modify the pod and then it will be persisted in that CD after going through. So now modification, this enables some of the really powerful use cases. One would be, let's say there are things that you want to do across your applications. One would be, let's say you want to inject a sidecar container for log collection. So you can do such a thing using mutating webhook. Or let's say for some other, let's say Istio is one where they use sidecar injection for the Envoy proxy and things like those. So another thing where mutating webhook is used, which is for defaulting. So if you have an API and user has not specified certain fields and you want to put in some sensible defaults, that would be another use case for mutating webhook. So we covered CRD and we covered admission webhook. And now let's go back and reconnect the dot with how do you manage a complex application which has managing day two operations are very unique to that application. So you take these three building blocks. First is you use the CRD to introduce the declarative APIs. Then you take all that operational knowledge of your application, which might be sitting either in playbooks or some bunch of bash script, or maybe sometimes in wiki pages. So you can take that operational knowledge, put that in the controllers, and with that, you will have a working API to manage your application. And now optionally, you can use admission webhooks. Now when it comes to orchestrating and managing all the workflows related to application, you can leverage all the Kubernetes primitives. You can, for service discovery, you can use the services. You can use pod, stateful set, or replica set for orchestrating, or what I call as infrastructure programming. You can use secrets and config map for configs and credential management. So you don't have to reinvent the wheel over there. And if you look at some of the built-in controllers are also done like that, where replica set is built on top of pods and deployment is built on top of replica set. So there's a hierarchy of resources there. So, and once you have that, you use the existing tools like kubecontrol to manage the application. So to the end users, it's built-in API pretty much for them. And that's the whole idea. And you get all the other features like authorization, authentication, and auditing that comes with the API for free. So with that, so now we know that, okay, these are the primitives available, and these are, you can build your custom controllers, application controllers to manage your application. Now let's look at how we can do that. So in this section, we'll be talking about Kubebuilder. So Kubebuilder is an open source project under Kubernetes org. It's actually a sub-project of special interest group API machinery. So the project was started about a year back, and we looked at the state of the art for writing custom controller at that point. And it was very complex. So you need to have deep understanding of low-level Kubernetes APIs to write something workable, and it required a lot of copying, pasting of code, which was very error-prone. And the documentation also was very fragmented and all over the place. So we looked at that problem and we said, how can we solve it? How we can make it really easy to extend Kubernetes? How we can take all those extension points and let people bring their expertise of writing, managing the application and pair it together with the extension points and make it easy to extend Kubernetes. So let's look at some of the components of Kubebuilder project. So the three main components. On top, you have this Kubebuilder CLI, which bootstraps a user project, and it will the day-to-day flow of either bootstrapping or adding new APIs and controllers or updating the dependencies in the project. That's done by the Kubebuilder project. And then there are two components, controller tools and Controller-runtime, which are used by the user project itself to implement the APIs and controllers. So let's look at the tools. What do they do? So the first is when you want to, let's say you decided to write an API and controller, you would start with an empty directory and you would like to bootstrap the project. So the first is set of commands which sets up the dependencies, sets up the right directory structure, looking at some of the things that we have learned over the past years by writing custom controllers. So we have baked those all in these tools. So what would the maker Docker file look like? And we'll scaffold the make file, which would pretty much have most common targets that you would use in day-to-day development of your controller. Then when it comes to adding APIs and controllers, scaffolding some of the boilerplate code automatically for you, wiring them up with the right set of underlying clients and libraries. So this is the part which Kubebuilder does, and then the controller tools is, so like we discussed about, CRDs are the way to introduce your API. So it has tools to generate the CRDs. So the tools basically look at the types.go, and we'll show you in the demo how that is done, and then CRD, generation of the CRDs. Then the last part is, which is when, let's say you have your controller ready, you want the manifest that you need for deploying in Kubernetes. So you have tools for generating those as well. And then this is the most important component of Kubebuilder, which is the controller runtime. Like I discussed before, the state of the art was copying and pasting the code. So we looked at some of the common patterns that you have to do when you're writing controllers. For example, you want to observe certain resources in Kubernetes. Then you want to invoke reconciliation. You want to run this active reconciliation loops. You want to run a number of threads over there. And so all those, some of the things that are common patterns, we abstracted them out and provided some intuitive APIs to use that. so that users don't have to worry about this low level. Underneath, it uses the low level Kubernetes upstream client libraries, but you get the more intuitive patterns that you can directly apply. Then another is very similarly, we extended it to admission and conversion webhooks, which the APIs. And then the third part, which we have seen that is which is is about providing a dynamic Kubernetes client, which can work with any Kubernetes resource. So that also makes things really easier to understand, because now you have a very less API surface area when it comes to client, which can talk to any resource. So essentially, the whole idea is that we are still iterating over these libraries, and as we are learning more and more about the best practices, we're trying to bake them in either in the core library or as in utility functions that people can use. And so another example is like when you are running your controller in the production, you want access to all the metrics to debug any production scenarios. So the controller-runtime library automatically provides some of the metrics like the reconciliation errors, the number of reconciliation, what is the backlog queue that you have in the reconciliation. So things like those are automatically supported. So I think with that, can we switch to the terminal? We would look at some of the Kubebuilder flow, and I will also show you controller tools and controller runtime abstract. So let's get started. Okay. So right now we are in a directory which we have already bootstrapped for our project, the SqIDB operator. And so let's say you have downloaded Kubebuilder release on your laptop, and after that, what you will get is Kubebuilder CLI on your command prompt. So you can basically, there are not much commands actually if you look at. So the first thing that you want to do is you want to invoke, you want to bootstrap your project. So the way to do it would be, I've already done it, so I'm just going to show the command here. So you just run kubebuilder init, which will initialize your project. It takes a bunch of parameters, like you can specify the license you want to include, what are the owners you want to use in the copy header file, copy header that shows up at the top of the file. Then once you have that, what you'll see is it will scaffold the project structure for you. So this is pretty much the structure that every Kubernetes project that you'll see follows. And so let's look at very quickly some of the things that it did for us. So it sets up the Go dependencies. You see the Go package lock and Go package toml file, which is, we're using GoDep for managing dependencies. So we set that up automatically so that all the Kubernetes dependencies gets pulled for you. So that gets pulled in the vendor directory here. Then look at, we automatically create a Docker file, scaffold the Docker file, which we'll use for building the controller image that we can run it in cluster. Then we scaffold the make file. I can quickly show you the make file. So make file has some of the common targets that you'll be invoking. So one example would be, you'll be scoping, let's say you want to run test, you want to build the manager binary, you want to run, you want to install CRDs in the cluster, you want to deploy the manifest, you want to, let's say, clean up all the manifests that you deployed. So all these common workflow, it automatically is available right off the bat when you run that command. Then let's show you a little bit of the code. So this is, we'll scaffold the main.go, which is the entry point for your controller, where it will read the config, which is the Kubernetes config, whether you are running on locally or in the cluster. It will automatically set that for you. Create the controller manager, which is basically a shell you can think, which is going to host all these controllers, a set of controllers. Because when you're writing API, you will be, you can have multiple set of controllers to power the same API, performing different functionalities. So then in the end, you just invoke manager start here. So let's go back. Now let's look at, so up till now, let's say this is the bootstrapping of the project. Then the next step would be you want to add an API. And API step would be you just run this command. Let's say, like in this case, we wanted to add an API called SqIDB. We wanted to add v1 alpha 1 and add this group. So we invoke Kubebuilder create API, and now it will create scaffold out the API and the controller files. So let's very quickly go over those. So package is where APIs and controller code lives. So in the APIs, you have infra and the v1 alpha 1. So let's look at one of the files. So this is your types.go for the Kubernetes API. Now it will start with, so this is our first API, let's say SqLDB. Like June explained earlier, every Kubernetes API have these fields, like it will have the type meta information, the object meta information, which is basically the metadata and type meta, and then the spec, and then the status. So spec is where it is all application dependent. What are the fields you want to take as input from users? So like in this case, the database type, the version of the database that you want to run, and then you can have different fields for the topology you want to set up, like the replicas and like the disk you want to use, things like those. So while we are here, I wanted to show, we talked about how controller tools is one of the tools that takes your types.go and it generates CRD schema. So you will see that these are Kubebuilder directives that you can specify in the code here. So like here, I'm using a feature of CRD, which is print column feature, which lets you decide what columns you want to print by default when a user performs kube control get on that resource. Like for pods, you see certain columns. For your own resource, you want to customize the output. So this is where you configure the feature for CRD, and controller tools is going to take this as input and generate the CRD YAML file. So for example, I can quickly show the config for this API, the CRD. So the CRD definition for SqLDB API that we added is, so this is generated, for example, the name of the CRDs here, like the printer column spec that I showed you earlier, this got generated in the form of here. So it's saying that, okay, show replica as one of the columns and get this as the JSON path for extracting that value that you want to show. So there are other features, like similarly, if you want to add more validation, you can annotate the fields in your types.go with the OpenAPI specific annotations, and the controller tools are going to generate the schema automatically for you. So this way your code is in sync with the CRD schema. So yeah, that was quick about the CRD schema. And then we can look at just very briefly at the controller code as well. So your controller code is, so like in this demo, we have two controllers, so SqLDB and SQL backup. So SqLDB controller here is where, so you'll see the controller runtime, the library part that I talked about earlier. So this is what is, we are importing that, and we are using, so the first thing controller wants to do is being able to observe the resources. So you will see that this requires just a simple, so we have these high level APIs where you can say, I want to watch this resource of kind this, or in this case, the three objects that we care about is the SqLDB, and SqLDB basically uses stateful set and services for orchestrating the SqLDB. So we are watching those resources as well. And then some of the things where you can set up the ownership hierarchy, which is, so with just few lines of code here, it will automatically set up, okay, it will trigger write objects that gets queued in the reconciliation for reconciliation. Now let's look at quickly how reconciliation code looks like. So typically, all you need to do is, if you add your watches correctly, then you can just focus on the reconcile function. And here, this can get this will actually depend on the complexity of the application you're managing. Like in this case, you'll first get whatever resource you need to reconcile. You want to probably default if this resource was not created, want to set up the defaults. You can do validation also here. Then So yeah, this code I will not actually go through this code in detail. So let's skip this. So this is where controller and API code is organized. So I think now this would be the right time to switch to the next part where let's look at the SqLDB operator. So June would be giving us the overview how the SqLDB operator that we wrote for this demo is set up. So June.
Okay. Thanks, Sunil, for the detailed explanation about Kubebuilder. In this session, we will show how Kubebuilder is used to create a simple operator, a simple stateful operator named SqIDB. Before diving deep into the demo, I wish to provide a high-level overview of what the operator does. The operator creates and manages a Postgres cluster. It comprises of two APIs. Like Sunil said, is a SqIDB API and the SQL Backup APIs. The SqIDB API is used for the creation and restore of the Postgres clusters. Well, the SQL Backup API is used for backup the data of the cluster. Underlying all the Postgres cluster created by the operator, we have a shared storage layer underneath. We use a network file system to store a backup file and then retrieve the backup file for the restoration purpose. We run the operator between a gKery cluster and create the manifest to create the SqIDB and the SQL backup resources. Our demo workflow is very simple. It comprises of only 3 steps. The first step is to create a SqIDB resource to roll out a cluster and wait for the Postgres cluster to become ready, and then we populate the data to it. Please note that for simplicity reasons, in our demo, we will only start one Postgres database instance. So a cluster means only one instance of a database. And in the second session, we will create a SQL backup resource to trigger the backup of the data that we inserted into the cluster in step 1. And lastly, we will create another SqIDB resource to roll out another cluster, and we will verify that the data of the old cluster can be restored to the second cluster. Yeah. Now let us go over the workflows for the Postgres database instance creation. What happens here is that the users create a SqIDB resource. When the controller observes the creation event, the controller creates a stateful set resource. Between spec of the stateful set resource, we specify the Postgres as the container image. And then the stateful set controller, one of the primitives that we went over in session 1, creates the pods. And between the pod, there is the main container running the Postgres database. And we use a Postgres-specific client named PSQL to access the container. This is done through a Kubernetes service resource. This service is a load balancer service that exposes the container to the client. And all of this information is hidden from the end users. All the end users have to do is very simple. Just by running the kubecutter apply, the manifest file, all the users have to do is to create the SqIDB resource, and that's it. For the backup workflow, what the users can do with the operator is that he or she can create a SQL backup resource. The backup resource has a reference back to the SqIDB resource that we created in the previous workflow. And with this information, the SQL backup controller is able to identify which container that it wants to run a command with. The controller will run a command within the container to trigger the backup utility to perform the backup. What happens here is that a backup file will be created by the utility and stored into the underlying network file system. Please note that for the network file system, we can substitute it for other storage mediums, such as the Google Cloud Storage and the Amazon S3 and Azure Storage. It is pluggable. It is interchangeable. And lastly, for the restore workflow, the users create the second DB resource. By this time, this DB resource has one additional API field that references back to the SQL backup resource. Why we want to do this? This because we want to get the backup file information from the backup resource. Using the backup file name, the SqIDB controller is able to fetch the correct backup file from the underlying network file system and then call the restore utility to perform the restoration. In the end, a new cluster will be created, and the cluster will be loaded with the backup data. And Sunil will show us all the workflows through a demo.
Okay, so I'm going to, let me attach to the demo mode. Okay. So with this, let's look at what we have. So right now I have a GKE cluster, and let me quickly check if we have connectivity here. So yeah, we have a 5-node cluster here, and we already have deployed the controller in the cluster. So let's look at the CRDs. The first step would be, let's look at the CRDs installed in the system. So we have already created 2 CRDs, which is SqLDBs and SqLDB backup. We can quickly look at one of the CRDs here. So yeah, you'll see whatever in the earlier part I showed the CR definition, that's where we see pretty much very similar to that here. So now the next step that you want to do is I'm going to show the config that we generated for, let's look at user wants to create a DB instance. So this is this this is the config that looks like for the DB instance, where you specify the name, you specify what version of the database you want to use, what type of database you want to use. In this case, we're using Postgres, and then the disk information for like what disk to use and all. So we can do, okay, before I dive into that, so on the right hand side, what I have is, think of this as another application which is running in the cluster, which is going to access the database which is provisioned by when we submit the resource, DB1 resource. So I'm going to apply DB1, and so you see that database request is accepted. We can examine the SqLDBs by running kubecontrol get here. So this is the part I was explaining earlier, where these are the columns that you can configure. So since it's a, yeah, so this became ready pretty fast. So let's look at, we can access this on this service endpoint. So status is one where, yeah, it is using the status field here. So we are using hard coding the credentials here. So we'll use that. Okay, so we are in, so you can see that what we did is we submitted the DB1 YAML file using kubecontrol, not using any new sort of tools to work with our database. And then we use the existing primitives like services to expose it. And if you look at it, it is using stateful set, so you can not here. If you look at it, it created a DB1 stateful set, which is actually running the Postgres pod and container inside it. So now let's look at, we want to take a backup, which is what the day 2 operation looks like. So for backup, we want to do is, let's say, this is also modeled as another API, SQL backup. And in this case, it's a very simple API. We're saying we want to just back up the DB1, and we want to save the output in this file. Now we can just apply this the similar way. So this is like a day 2 operation you can imagine, which is taking a backup. And oh, okay, sorry. So the backup is succeeded. So yeah, I mean, depending on the application, you can output whatever things you want to output here. So now the third step is, which is we want to restore, which is another day N operation that we want to perform. So restoration workflow, so what we want to do is we'll be using DB2 here. We want to bring another instance. We want to restore from the backup that we took earlier, and we'll just use the backup name DB1 backup here. So we just apply this, and so yeah, so with that we see DB2 is also ready. And maybe here additional things could be done is that this was restored from this DB or additional data that can be shown here. Now, oh, okay, we did not create any entry in the previous before taking backup. So yeah, the idea was actually we'll create some data and then we'll take the backup and then we'll restore it. We can still do that. I think we have time. So let's create some entries here. Okay. So I'm still connected to the DB1 if you look at. So DB1 has this.
In this case, you have to delete the DB2 and then create it again.
Yeah, we can actually delete. So that is another thing which, so we deleted the DB2 and we want to take backup as well. So let's delete backup as well.
Yes.
Okay, so now we want to take the backup. Let's do that. Oh, sorry.
You should check the secret backup details.
So yeah, backup is succeeded. So now we create the DB2 here. So we'll just repeating the same thing here. And this should restore from the backup that we took earlier. And we can look at, okay, so DB2 is also ready. So now what we can do is,
do you want to check again?
let's connect to DB2. June is not feeling confident, but let's see. So, okay, yeah, we have that row. So yeah, it's working. Okay, so
SqIDB again to show the server restore.
oh, okay.
The status.
Yeah, it is ready. Server restored.
Yeah. As you can see, the status of a DB2 has changed to server restore.
Oh, okay. I see what you mean there. Okay. Yeah, so with that, you looked at the day 0 and day n operation, what it looked like for an example. So this is not a production-ready SqLDB operator, so please don't use that in. Yeah. So I think with this, it's pretty much the end of our session. So can we switch back to the slide? And I want to go over the takeaways real quick. Yeah, so the takeaways that I would like to mention over here is the first is that Kubernetes offers really powerful API extension mechanisms. And if you look at some of the product launches that have happened at GCP, like in the past or now, Istio or Knative, all these are built on top of those extension points. So that's the first takeaway. The second one is you can manage complex application using operator pattern, the one that we showed earlier, by extending Kubernetes. That's a key takeaway. And the third is the Kubebuilder SDK, which provides you all the tools and the libraries to extend Kubernetes. So yeah, with that, I would leave you with this slide where we have all the links to the resources that we saw today. The operator code, the Kubebuilder book, also this. So Kubebuilder has an active Slack channel, so I've also put in the link for that. If you have any queries, you can jump on the Slack channel and ask about it. And the code that we showed today is also open sourced under Google Cloud Platform Kate's SqLDB operator. So go through that. And then we have mine and June's GitHub handle and Twitter handle as well. So feel free to reach out.